Welcome back to Math 432. We're discussing the binomial theorem, which I'll remind you says that x plus y to the power n is the sum from k equals 0 to n of n choose k, x to the k, y to the n minus k. We're going to be doing a slew of examples, applications of this theorem. Here's one. 2 to the n is the sum from k equals 0 to n of n choose k. Why is that the case? Well, we could take, in the binomial theorem, we could just set x equals y equals 1. These are variables. We can take values. When we plug in these values, this is a polynomial, so this is a completely legitimate thing to do. What do we get? On the left-hand side, we get 1 plus 1 to the power n is equal to the sum of k equals 0 to n choose k, 1 to the k, 1 to the n minus k. So simplifying this out, we exactly get 2 to the n is equal to the sum from k equals 0 to n of n choose k. That's a rather uninspiring proof, but it's a fairly powerful technique. Let's also think, though, if we were going to give this a combinatorial proof. We did that actually last time when we were looking at penguins and polar bears. But let me just remind you of it because it's really important to be able to apply this technique of interpreting both sides as sort of the same thing. So here, it's pretty easy to choose subsets. That's really what we're doing. So I want to think of subsets in a more, narrative way. So I'm going to think of committees, okay? So I'm going to think both sides are telling me how to choose a committee with n potential members. Okay, that's what I claim they're both doing. This is a counting in two ways kind of proof. The left-hand side goes person by person, in or out, or on or off. Are you on the committee or are you off the committee? I've got 2 to the n choices. Okay, what does this side do? This says pick a size that you want your committee to be. That size is what we're going to call the parameter k, and then choose that many people. So you can either go person by person and say you're in, you're out, you're in, you're out, or you can choose how big you want your committee to be first and then fill up your committee. Either way, you've chosen a committee from among 10 potential people, and it gives us a combinatorial proof of this identity. So the second identity that we looked at when we were doing the same example with the penguin and the polar bears was this one. 3 to the n equals the sum n choose k, 2 to the k. Why would that be the case? So again, let's do two proofs. The binomial theorem. The binomial theorem says what? Well, here I want to get 3 to the n, but there are lots of ways to get 3 by adding two numbers. So that's not the side that's going to help me figure out how to apply the binomial theorem. It's really this side. I've got my binomial coefficient, which tells me the binomial theorem applies, and I've got 2 to the k, so I know what x is. X is 2. I don't see y, so y must be 1, because I don't see it. And 1 to a power is just 1. So this is what I'm going to plug in, and when I do this, exactly what I get is, well, 2 plus 1 to the n is equal to the sum k equals 0 to n choose k, 2 to the k, 1 to the n minus k, which is exactly this identity. Okay, so that works pretty well plugging in with the binomial coefficient. Even though we did the couples problem, the penguin couple problem, to get this identity last time, we can still think of it in a similar way this time, as we can think of it as a committee, and we can think of it a committee-style problem, okay? And what you're going to do is we're going to designate, so we're going to think of, we're choosing a committee, and this way we're going to go through each person and decide, are they going to be on the left side of the committee or the right side of the committee, or not on the committee? There need to be 3 choices, okay? So what we're going to, maybe I'll write my interpretation in green. So we have a committee that we're forming with n potential members. And here I want to think of them as they're on the left, right, or off the committee. Okay, so maybe I think of my committee as having 2 sides, or maybe there's 2 teams or something that I'm playing, and you're either playing on the one team, the other team, or you're not playing at all. Those are my 3 choices. And then I'm going to count in 2 ways, the same way that I did over here. So the left-hand side is going to be the easier one here. So the left-hand side, how is it counting my committee? You go person by person to decide. And again, there are 3 choices for each person. There are n people, so I get 3 to the n. So that's correct. For the right-hand side, we're not going to go person by person. We're going to form the structure of our committee instead. That's where the parameter k is. So choose the size of the committee. Choose the size first. This is your parameter k. It's going from 0 to n. You can have as big or small of a committee as you want. Okay, and then you're going to pick members. Pick members who are on the committee. So that's saying this didn't happen, but I still have to choose this way and then put each on a side. Put each member on a side. And that's how we're going to get this part of the identity. So again, the binomial theorem is incredibly powerful. We can often prove things with it, but we often want to have this combinatorial description as well, because that's going to help reinforce the idea of what and approach certain problems where it may be harder or less obvious how to apply the binomial theorem. But let's do one final application of the binomial theorem, which is a really interesting one, which is that the number of subsets that have even size is the same as the number of subsets that have odd size. So that might seem a little strange, but let's think about it with our 4 members here. So if we have 4 objects, so let's do the example, and let's just see that this is true, because it's kind of a weird statement, so we want to really ground it. So we've got 4 objects, and we want to say, okay, we can have subsets of different sizes. So what size could my subsets be? Typically, we're going to call those k. So k is my subset size, and then n choose k is how big it is, right? So I could have 0, 1, 2, 3, or 4. Remember, the only interesting one here for 4 was 4 choose 2 is 6. 4 choose 1, there are 4 options. If you want to choose nothing, there's one way to choose nothing. If you want to choose 3 of the bugs, well, then you could just as easily pick the bug to leave out. And if you want to choose all of the bugs, there's one way to take everything. Okay? And so what this statement is telling us is that if we think about parity here, we think about k, so here is an even guy, here is an even guy, here is an even guy. It's telling us that 1 plus 6 plus 1, this is the total number of subsets that have an even size. This is going to have to equal the total number of subsets of an odd size, which is 4 plus 4. And in fact, they are both equal to 8. So, yes, the statement's true. But the question is, how do we see this? Well, we could try to say, okay, well, how do we line up and maybe come up with a bijection to take a bug out, make the subset smaller, something like that. And that's possible to do, but it's a little bit cumbersome and it's a little bit challenging to do it that way. So let's do it a different way, and let's use the binomial theorem. So here's our binomial theorem once again. And how can we prove this with the binomial theorem? So the thing to figure out is, well, how are we counting these guys? We're saying that something's equal to something else. Well, that's the same as saying a difference is 0. Another way to see that, just to maybe give you some intuition for how I'm coming up with this, is how would I count the blue amount? So the number of subsets, number of even size subsets. What is that? That's the sum, k even, of n choose k. Okay, and what's the number of odd size subsets? It is the sum over k odd of n choose k. So to say this equals that, another way that I could say it is their difference is 0. So watch what happens in the binomial theorem when I take x equals let's let x be minus 1 and y equal 1. Then what do I get in the binomial theorem? I get minus 1 plus 1, which is 0, is equal to the sum from k equals 0 to n of minus 1 to the k and choose k. Right? The y goes away, the x becomes a minus 1 to the k. So here, when k is even, I'm going to get this. And when k is odd, I'm going to get this, but with a negative sign. So this minus this is 0 is the same thing as saying that these two amounts are equal. So you can get kind of surprising combinatorial statements that don't seem that obvious. I mean, yes, okay, 1 plus 6 plus 1 is obviously 4 plus 4, but not in any kind of obvious way, right? I didn't know that adding up every other number like that would work. But when I think about it in terms of the binomial coefficient, if I just try to figure out how to balance things out, then I can come up with an identity.